All right, hey, how's it going, everybody? Mr. Fortin here, checking it out, doing some asynchronous problem set with you guys here. I haven't done one of these videos in a while, but I gave some problems. I think about 5 problems. That's right, it's my gift to you. Practice some Algebra 1 today that I want you to work on. These come from Chapter 8 of your textbook. I know we're not really doing the textbook this year, but we're covering most of the stuff that's in the textbook. So at this point, we've touched on pretty much everything that's in this problem set. A couple of these problems are a little bit of a preview of our next unit, which is going to be quadratic equations. And you're going to learn some skills when we do quadratic equations that are going to help you with parabolas, some of the graphing problems coming up later. So anyways, I'm just going to do these with you to help you out because I'm anticipating you guys to get a little tripped up, a little stumped, right? And be like, I kind of have an idea what to do here, but I'm not totally sure. Like this is definitely a question here, 8-113, that a lot of people kind of don't really piece together. Find it a little bit hard here, okay? Because it deals with percentages here. So we're gonna do all these problems together right now, or you can just pick and choose what you wanna watch. You can watch the problems you don't get after you try the first time here. 8-113, price of milk has been steadily increasing 5% per year. We got ourselves a change number. So at this point, you're thinking 5% per year. Well, I'm changing. Does that mean going up by $5 a year? What? No, not 5%. Okay, we'll get back to that later. If the cost of the gallon is now in 2021, $3.89, and it's been going up 5% of the year, we got to think about how it's changing because what will it cost in 10 years? So at this point, you should be thinking, well, if I'm going up by 5%, what exactly does that mean? I get 5% higher. Well, it means that this is 3.89. We're going to get 0.05 higher than that. So this kind of get 0.05 higher than that. So that means that this is actually going to be an exponential situation, right? Because it's going to get 0.05 higher. So we have that weird situation where we got to remember we have that $3.89. I want to get 0.5 higher. So I can't just multiply by 0.5, right? If I have 3.89, remember 5% written as a decimal, right? 5% written as a decimal. You do this thing, right? You get rid of this and you move it 2 decimal places over. Remember that trick? Because remember, percent, 5% means 5 per every 100, right? Or 5 per every 100, right? Percent, per century, per 100, 5 every 100. Oops, 5 for every 100. This is how you write 5% as a decimal, 0.05, okay? So I can't, though, take 5%, convert it to 0.05. I can't just multiply it by $3.89 and say that's what's going to cost a year from now, 5% higher, right? Because what am I going to get? Well, 0.05, that's a tiny, tiny number. It's way less than 1. And if I multiply it by 3.89, oops, well, whatever, I'll just stick with that. I get like 19 cents, okay? That doesn't make sense. So the thing you need to remember is that if something is increasing by 5%, okay, remember, we start with 303.89 here. That is 100% of the current value, 100% of the current value. This is 100% here. We want to raise it by 5%. So we want to multiply by every year, if we're increasing by 5%, is that we want to multiply that by 3.89 and multiply it by that 100%, but then 5% more than that. Because at the end of the day, if it's 3.89 right now, and that's what it costs right now, that's 100% of the cost right now. We want to find 105% of the cost a year from now, okay? And that becomes my multiplier here, okay? So we want to multiply by 105% to figure out what it costs next year. That way you're going to maintain the value. You're going to take that $3.89, and you're going to increase it by 5%. 105% is 5% higher than 100. Okay, and that's basically the idea. Kind of ugly here. Okay, so this is an exponential function. If I were to write this in function notation, check it out. This is how I'd write this in function notation. I'd write it like this. F of x, function of x, is, well, we have to take our starting value, $3.89, and multiply it by 1.05 every single year, right? Every single year, and that's where my x variable is here, okay? Let x equal number of years from now. Okay, and there we have it. So how are we going to make it figure out what it's going to cost in 10 years? Well, we'll take, right, we want to find it in 10 years. Function of 10, right, of 10 here. Output, when the input is 10, is going to be 3.89 times by 1.05. And we're going to do that 10 times. We're going to multiply by 105% 10 times in a row, because after 1 year, it'll be 5% higher. After 2 years, it'll be 5% higher. So we'd have to multiply by 1.05 again. After 3 years, it'll be 5% higher. So we have to multiply by 1.05 a third time. We're going to have to do that 10 times. I have to do that 10 times here, okay? So what this is going to equal, I'm going to do my approximately here because it's probably going to have a lot of decimals here. 1.05 to the 10th power, ooh, that's a lot here, okay? So if I'm going to do this in my Macintosh Apple calculator that I have here, I got to remember my order of operations, okay? PEMDAS, right? PEMDAS. How am I going to figure this? How am I going to evaluate this? Simplify to figure out exactly what this represents. I got to remember PEMDAS. There are no parentheses. That's not. What about exponent? Okay, parentheses, exponent, multiplication, division, addition, subtraction, PEMDAS. Okay, so 1.05 to the 10th power, I'm going to do that, and I'm going to get this. So exponent first, okay, that's what 1.05 to the 10th power equals, and then I'm going to multiply that, right, because it goes exponent, multiply in PEMDAS, okay? 3.89 times by about 1.62, okay, I'm going to multiply that by the starting value, right, which was 3.89, what it currently costs here, okay, and I get about $6.34, okay, $6.34. Okay, that's what I get. Okay, so it says here, the premise of this problem is that it has been increasing steadily, 5% per year. We assume it continues. So in 10 years, that's how much it's going to be worth here. But if it's been already increasing for several years at 5% per year, the question is, what did it cost 5 years ago? Right, 5 years ago. Well, if X is the number of years from now, what can we plug in for X to represent 5 years ago? So not 5 years from now, that would be 5 years from now would just be 5. 5 years ago is, we can have a negative exponent there. Yes. So if I do f of -5, that's going to tell me what it cost 5 years ago. We're going to undo all those 5% increases. Math is cool, man. Math, we can solve this stuff out. 3.89 times by 1.05 to the -5 power. And that's how we do it. Bang, we got it here. Man, I love math, right? I love math. Why would I be doing this job if I didn't love math here? All right, 1.05, take it to the, this is y to the x. I don't know what that does here. This is, I'm doing x to the y. Take it to the -5th power, so I get 5, and then I'm going to make it negative. And that's what we got there, okay, right? So remember, negative exponent is repeated division of this here. So I could have done 3.89 divide by 1.05, divide by 1.05, divide by 1.05, divide by 1.05, divide by 1.05 5 times. But anyways, this is just might be easier to 1.05 to the -5th power. Get this, multiply by 3.89, and I get that. I get $3.04. Okay, does my answer make sense? Yes, it does. Okay, yes, it does, because the value's been increasing by 5% every year. So if it's currently $3.85, 89 cents, yeah, it probably was about $3 or so 5 years ago. That's pretty big inflation, 5% per year. That's called inflation. You have to learn about inflation yet? It's about your money. It's worth less year over year. But inflation in the U.S. is only really like a 1% or 2% or so. It's a little bit higher than it had been previous years. Printing off money in our country. So anyways, I think it's a little over 2% now. It's a little bit high. For the last few decades, it hasn't really been that high. All right, anyways, use the graph at right to answer the questions below. Okay, hopefully you got this. Message me if you have any questions. Okay, use the graph at right to answer the questions below. One of the lines represents Feng, another one of the lines represents Wei. Write an equation for each girl's line. The two girls are riding bikes. How fast is each girl riding? So let's do it in order. Let's do A. Okay, so this is pretty easy. Starting value 0. Starting value here, -12. Okay, so I know I'm going to have this. So Feng will do up here, Wei will do over here. I know I'm going to have -12 for Wei, so -12 is going to be my starting number. 0 is going to be my starting number here for Wei. Now I need my slope. Okay, these are lines, linear functions. Oh, linear functions, so much easier than the functions we've been dealing with recently. Okay, find some lattice points. Here's a lattice point right there. There we go, slope triangle. We'd rise 18. Okay, and we'd run 18 over 5. Does that make sense? I don't know about that. Is it 18 over 5? I don't, maybe that wasn't a lattice point here. 18, huh. I think I'm doing something wrong here. 18, what are they scaling by? Oh, this is 4.5. 18 over, that's messy here. There, let's not do that one. You guys are probably doing this one. Oh, no, this is 1.5. Oh, this is actually, it made this a little, I think this is kind of tricky for you guys here. Oh, let's do this one. This lattice point's probably pretty good here because now we can divide cleanly, okay? The reason why I struggle with this one here is that, check it out, look at your x-axis. So you need to scale your axes consistently, okay? That means choose one thing to scale the x-axis by, and then you can scale by something differently on the y-axis, but it needs to be consistent. The y-axis is scaled by 3s, okay? The x-axis, so that we can look at these, analyze these graphs a little more cleanly, it's scaled by 0.5. So look, 0.5, 1, 1.5, 2. There's our 2 right there. 2.5, 3, 3.5, 4. We got a 4 right there. So this slope triangle that I just did here for Way's line right here is rise plus 24 and run plus 6. Okay, plus 6 here. And what do we got for 24 over 6? 24 divided by 6 is 4. So what I got here for my equation for, oops, not, yeah, this is for Feng. Okay, my bad. Feng here is y equals 4x. Okay, there's Feng. And then Wei is the one who had the negative x-intercept. And you know what? This actually is where they meet here on the graph here. So I'm just going to add 12 to that. Okay, so if I have this whole thing here, there's my rise. It'll be the same run. It'll be over 6. This will be 24 plus 12. This is 36 here. Okay, we're going from negative 12 all the way up to 24. This is 36. Okay, so 36. The slope of Ways is more steep. It's more extreme here. So it's 36 divided by 6, and it's 6. Okay, so I got this for Way. Y equals this. I apologize if I'm pronouncing that incorrectly. Feel free to tell me. Please do tell me. I'm sorry if I did. The two girls are riding bikes, and how fast does each girl ride? Well, speed is a unit of measure. Sorry, a unit rate. Right, we're going to find a unit rate here. So we can get that from our slopes. Okay, what's going to tell us here? Remember this. Remember our chapter 2. Slopes tell us the speed, right? The speed at which, because this is distance over time is the measurement of speed. How does it change? Rise over run, okay? So our rise here was plus 24 miles for every plus 6 hours, okay? 24 miles every 6 hours is how many miles per hour? Well, it's 4 miles per hour, okay? So for Feng's speed is 4 miles per hour, or mph, right? Mph. Here is how you might abbreviate that slope, that rate of change, that speed of Feng. And then with Wei, we have 6 mph. Okay, we just get it from the slope there. But you need units for sure. Okay, speed is in 4. Like, what the heck are you talking about? Kilometers per hour, inches per hour, or miles per hour. Okay, and then so that's I got for Wei, I got for Feng the speed. Okay, when do Feng and Wei meet? At that point, how far are they from the school? Okay, they meet right here. All right, this is just breaking down a graph. Yeah, these are definitely gonna ask questions about these in the future for sure. After you're done with Mr. Fortin here. Okay, they meet right here. It looks like they meet this point. This coordinate pair is x is 6. And y is 24. I really looked at this one a lot. So where do they meet? When do they meet? That's a time. When is a reference to what time, right? When is when do we get there? At the time, it's going to be 6 hours into the race. Okay, 6 hours into the bike ride. They are both 24 miles from school. You know, they never say what direction these girls are riding, so it's possible they never meet. So a better way of writing this question would be like, when are they the same distance away from the school? I mean, or they should have said they're going the same exact direction. When do they meet? When do they pass each other? There's your answer there. All right, cool. Check this one out here. 8-1-15. Hey, I'm grooving. Not so bad. Hopefully you watch those. You know, definitely anticipate some folks struggling with those last few problems. Hopefully it helped you out. Again, practice, get through problems, ask questions. Yes. Okay, graph this one. Identify the y-intercept, x-intercepts, and vertex. You might stumble on this one and be like, whoa, this looks similar to something we did yesterday, okay? Hey, what form, guys, is this written in? Okay, what form is that here? It's quadratic, right? Because we see x as being squared. That's nice here, x being squared. What form is it written in? Well, this is the thing you got to remember from the beginning of classes. I know you just got back from spring break. What form is written in? Well, there are no sets of parentheses here. No sets of parentheses. So that's how you can tell the difference between standard form, factored form, and vertex form of a quadratic functions equation, okay? No parentheses at standard form. So now we got to remember from yesterday's class, what is standard form good for telling us? Well, it tells you the stretch factor. It tells you which direction it opens and faster, if it's wide or if it's skinny, that's going to be your A. This is just going to be a, one, invisible one up here. So this is going to be the same as the paragraph. It's going to open up. It's not going to be particularly skinny. It's not going to be particularly wide. Then what else does standard form tell you? Well, the B doesn't tell you much right now. B kind of, right, moves it left and right, up and down. We're not sure. So with that -2 isn't worth talking about. How do I get my y-intercept from standard form? Okay, well, standard form is this. Y equals ax squared plus bx plus c. Where was the y-intercept? Right. If you remember from yesterday's class, it's C. It's this guy right here. Remember, 0, comma C. Oops. 0, comma C. And I put this down. I put this down as a note to you. I put it as a comment on yesterday's assignment as you were doing it, or class ended. I just wrote it. I was like, okay, it might have been tough to sort of follow the wrap-up that we had in class. Here's what to take away here. Standard form, good at showing you the stretch factor, right? And that's A, and which direction it opens. And then the y-intercept, there it is. Standard form, good at y-intercept. So now we have vertex form, good for vertex. Factor form, good to get the x-intercepts. And you can find the line of symmetry pretty easily if you have the x-intercepts. Standard form, good for the y-intercept. They're all good for different reasons, okay? Y-intercept here, well here, this is in standard form. Oh, we're missing something. Well, wouldn't this just be +0? Wouldn't my constant here, the x to the 0th power term, wouldn't it just be 0, x to the 0th power, right? We don't see anything. Okay, so that means my x-intercept here, my y-intercept, ooh, this is going to be tricky for the x-intercepts here. My y-intercept is going to be at 0, 0. Okay, 0, 0. Wait a second, this is 0, 0. Is that also an x-intercept? Yeah, it is. It's also an x-intercept. X-intercept also going to be at 0, 0. But wait. Don't we usually have 2 x-intercepts? Not just 1, but 2. Yeah, we do. We do. Check it out. I'm going to show you a neat little trick here. Let's take this. Okay, let me take this, and let's look at it down here. Okay, we have this. Y equals x squared plus 2x. Oh, sorry, minus 2x. There's a way for us to change this from what form is that again? It's the standard form. We can change this into a different form that can help find us our other x-intercept. What form of a quadratic function is good for finding x-intercepts? Is it the standard form? No, we just had that. It's good for y-intercept. Is it the vertex form? No, it's good for vertex. What about factored form? Factored form is great for finding the x-intercept. So the question is, we've studied this. We studied this right before we started this unit. Can you factor this? Can you factor this? So maybe we can get this parabola's equation written in factored form. And this is x squared minus 2x. What's the common factor? Yeah, common factor here is x. This is equivalent. X squared minus 2x is equivalent to x times by x minus 2. There you go, right? This is, if we look at this in terms of tiles, right? In terms of a generic rectangle here, this would just be height x with x minus 2. This is the product, x times by x minus 2. This is the sum, x squared minus 2x. Okay, right here is what we see right there. Outside is what we see right there. And there we go, okay? So this should tell us, right, that we have one x-intercept because of this guy right here. If x were 0, y is going to be 0 because 0 times by -2 equals 0. What's my other x-intercept? What was going to make this be 0? What would I have to put in for x here that would make this 0? We'll find a 0 on the graph, right? An x-intercept. Okay, the value of x when y equals 0. X is going to have to be 2. Okay, 2, 0 is my other x-intercept. Okay, this is 2, 0 because if x were 2 here, right? 2 minus 2 equals 0, and 2 times by 0, y is going to have to equal 0. Okay, so that's why this works here. Okay, there's my x-intercepts. We got that. Vertex. Ooh, there's a lot of work on this one. Ooh, it's a Tuesday asynchronous class set. I'm making you guys think. I'm making you guys do lots of work here. Here's where getting the vertex here, you got to remember, once I have my roots, my x-intercept, sorry, my zeros here, I can figure out where the line of symmetry is. Once I have the line of symmetry, I get my vertex. Remember this? This is a little tricky. Well, if I have my roots at 2 and 0, right? I got a root here at 2, root here at 0. Where is my vertex? Well, it's going to have to be a 1, right? It's going to have to be a 1 because the idea of this is that line of symmetry, to find the line of symmetry, it's just going to be over the x value that is the average of the two x-intercepts, right? Remember, we have symmetry of these parabolas. So if I have x-intercepts here, go to here, right? And right in the middle is going to be my vertex, somewhere up or down that line of symmetry here. So I simply got to take my roots and average them. Take my zeros here, my x-intercepts, and average them. 2 plus 0 divided by 2. And this is just 2 divided by 2, so it equals 1. We have a line of symmetry at x equals 1. Okay? And because the vertex is always on the line of symmetry, it's a lot of information here, right? A lot to keep track of. Keep going. You can do it. Okay? I can use that line of symmetry at x equals 1 to figure out where my y-coordinate is of the vertex. Figure out where exactly on that line of symmetry my vertex has to be. Then I can do that by going back to my original equation. Okay? Plug in there. Y equals, well, I'm going to do 1 squared. Okay? Minus 2 times by 1, right? Y equals x squared minus 2x. Y equals x squared minus 2x when x is the line of symmetry, right? That value here. So I get y equals 1 squared is 1 minus 2, negative 1. Okay, negative 1 here. So my vertex is at 1, negative 1. And do I have enough to graph this now? Let's check it out here. Let's see if I do, okay? Well, I got the vertex here. Okay, we already kind of have it identified here. Might as well graph it, though. Whew, run out of space here. Well, this is good. They're all kind of like, I'm just going to scale it normally here. So let's scale by 1. This is my x-axis and my y-axis here. We're going to have, definitely have an x-intercept and y-intercept. So this is an x-int and y-int. Okay, and then we have 1, negative 1. So sure, let's just scale by 1s here. 1, negative 1. This is going to be my vertex. Okay, and then I have another x-intercept here at 2, 0. Okay, and I've labeled it up. I labeled my x-intercepts, I labeled my y-intercept, and I labeled my vertex. And now I just need to, and maybe I'll make this be a bigger pen, draw in the graph. There's your parabola. This is the parabola of y equals x squared minus 2x. Oh, we're thinking so much. Mr. Ford is doing this on Monday after first day back at spring break. He's like, why did I give you so much work? Whoa, dropped my pen here. All right, man, you ever think your teachers are losing their minds this year? Lose my hair, I'll tell you that. Anyways, closure 8.6. Oh, what did you make this? 8.116. Find the coordinates of the y-intercept. Wait, coordinates of the y-intercept. Well, that's easy. This is in standard form too. So my y-intercept is at 0, negative 15. Okay, x-intercepts here. Okay, show all the work to use to find these points. So here, hey, I'm giving you a heads up. We're not going to go over this until next week, at the earliest, as a matter of fact. But you might as well. This isn't super hard. Somebody try this today. Stay with you late, Lissy. That's right. I'm calling your name right now. Lissy is like, I can find the x-intercepts by factoring here. We talked about this, which is a good idea. But sometimes it's not factorable. It's hard to get the x-intercepts. But anyways, if you factor this, change it from standard form. Okay, this is standard form. Okay, reminder, standard form, it's good for what? Good for the y-intercept. Not good for the x-intercept, but it's good for your y-intercept. So we got that, okay? And then what if we knew the factored form, okay? Factored form is good for finding the x-intercept. Okay, so actually, we know the equation of this parabola, right? This quadratic function, this quadratic relationship. We know this equation in standard form. We can go between forms, which is what we're going to do next week a bit here. We're going to change from standard form to factored form. Once we have that, we got those x-intercepts. Okay, so we check this one off the list. We've already done that. We need to get the x-intercepts. We're going to factor this. Okay, remember factoring? Hopefully remember factoring. It's coming back. We're not going to just forget it because we did it already. Okay, I put my x squared here. I put my negative 15 here. I set up my diamond. Okay, Remember, my diagonal here needs to multiply the same thing this diagonal will. I just need to figure out where to put my x's, where my negative 2x's are going to go. So I'm going to put negative 15x squared because that's what this diagonal multiplies to. This is going to also have to multiply to negative 15x squared. But it's also going to have to add to negative 2x here, okay? So 15, it's not going to be 1 and 15. That's not going to bring me to negative 2x. What about other things that go into 15? Well, it ends with 5, so what about 5? 5 times 3. 5 times 3 is good because if I do positive 3x times by negative 5x, 3 times negative 5 is negative 15. X times x is x squared, so multiply to negative 15x squared. But if I do 3x plus negative 5x, I get negative 2x. And we're good to go. That's how I can set up my generic rectangle. And this is going to be a rectangle, right? Freaking set up like this. Area as a sum, that's your standard form, okay? And areas of product is what I need to find my factored form, okay? That's what I'm trying to find right here to help me figure out where my x-intercepts are, okay? So I get x here, x times x is x squared, x plus 3, so 3 times x is 3x, minus 5. It's easy as that. Look at that. Negative 5 times x is negative 5x. Negative 5 times 3, negative 15. It works. Perfect, okay? So now I got this, I got this. Those are my factors. X minus 5 times by x plus 3 is the factor form of the same exact freaking parabola. So now I can use that to determine, okay, determine that the inverses of these, the opposites of these here, right? 5, 0, the additive inverses are the opposites. 5, 0, and negative 3, 0 are the x-intercepts. And I got that. I'm good to go. Okay, and last one here. Hey, I'm getting through this video faster than I thought I would. I was like, oh man, it's going to take like 40 minutes to explain all these. Again, you're just picking and choosing what you're watching, or you could watch the whole thing and hang out with me this Tuesday. Sure, why the heck not? Virtual school is a weird thing. Without using a calculator, simplify only using positive exponents. Okay, so here we're going to use our tricks, right? Tricks of the trade we got here. All right, 9 to the 1/2 power. What the heck is that? You guys remember that? You guys remember doing fractional exponents? Well, remember, hold on, 9 to the 1/2 power times by 9 to the 1/2 power. Remember this from first semester? That equals what? Well, if you're going to have the same base, what do you do to the exponents? Oh, that's right, you add them together. 9 to the 1/2 plus, right? Remember that was that rule here. Okay, so that equals 9. Wait, so 9 to the 1/2 power times 9 to the 1/2 power has to equal 9 based on the product rule, the multiplication rule of exponents here, right? Because you add the rules, you add the exponents together. This is 9 to the first, right? That would equal 9. Okay, so then what must 9 to the first equal? This right here. Well, 9 to the first times 9 to the first equals 9. What else times itself equals 9? Well, 3 equals 9, okay? Right? So this is 3 is the same thing as square root of 9. 9 to the 1/2 power is the same thing as the square root of 9. Okay? So remember here, something in the denominator is the same thing as the roots. Okay? Power over roots. 9 to the first power, and then take the square root of that. That's how that gets read here. 9 to the first power, take the square root. Well, 9 to the first power is just 9. Take the square root of 9. That's 3. Okay? So this is going to be 3 times by x squared times by y. I'm just going to maybe simplify it down here. This is 27 to the 1/3 power, so this is kind of the same thing here too, where what's the cube root of 27? What times itself 3 times in a row is 27? Well, that's just 3, right? That's just 3, right? Because 27 right here, that's just 3 times by 3. And if I take the third root of that, right, just grab one of those, equals 3. Goes away. Okay, so now this is also 3 times y to the negative 1. So now we're going to have an x squared for sure here because there are no other x terms here, or x variables, that is here. This whole thing would technically be a term. 3 times 3 is 9. Okay, x squared, right? No other x's, so we're not going to simplify that any further than x squared. But y times y to the negative 1 power. Remember, y is y to the first. And remember, you have to add exponents, okay? And what is 1 plus negative 1? Well, it equals 0, okay? So here, these are going to just cancel each other out. There's no y to the 0th power. That's just equal to 1. Anything to the 0th power is equal to 1. So man, there were a lot to think about in that problem. Okay, here's the square root of x taken to the negative. Negative. This is a tricky problem here. Simplify. You're only using positive exponents. So Hey, remember, this is the power rule. Okay, remember, right? Power to a power. When you do a power to a power, you multiply powers. That's a shortcut that we talked about first semester. Okay, so negative a half times, sorry, half times by -2. Well, -1/2 times by 2/1. That's going to equal -2/2. That would equal -1. Okay, so this is going to be equal to x to the -1, but then the rule says only positive exponents. So we're going to take the inverse of that. Right, put it in the denominator. Remember, a negative exponent means repeated division. Move it denominator, because that's what divide. This is the division bar, technically, is what a fraction bar does. Okay. Ooh, these are tricky. Emma's gonna have a lot of work correcting these. Sorry, Emma. Anyways, let's check this one out here. Okay, so this is another tricky one here. Remember, it's power over roots. Okay, power over roots. So, man, you could square everything first. I don't really do that. I might break this up. That's how I would tackle this problem. I would do this: 1/125. Okay, take that to the 1/3 power times by 2. Okay, right? This is the same thing. This is 2/3 rewritten a little differently. 2 times by 1/3 is the same thing as 2/3. You got 1/3, you double it, you get 2/3. Right? So if you write it this way, here now, oh man, sorry, Emma. You got a lot to. You probably correct a lot of things. Be like, watch Mr. Ford's video, but check it out. This is a little tricky. Here we got to think what number times itself would equal 125 3 times. What's the cube root? Ah, 1/125 actually does have a cube root, right? Because, right, the cube root of 125, right? This here, 1/125 is the same thing as 1/5 times by 1/5, right? That would be 1/25. And then 1/25 times by 5 would be 125. So here, this would be, right? I'm showing too much work here, but hopefully I win you over. The cube root of 125 equals 1/5. Okay, 1/5 times itself. Well, this is 25 times by 25 would equal 1/125. Okay. Ugh. You're tired, man. You're tired. You're like, really? 9 a.m. Mr. Ford decided to give this to me? Oh gosh. Okay. All right. This is 1/5. All right, so this is right. This becomes 1/5 here. We saw that to squaring to do. Okay, remember, power over root, power over root, power over root. That's how fractional exponents work. Okay, so now this is 1/5. Square it. That's 1/5 times by 1/5. Okay, 1 times 1 is 1. 5 times 5 is 25. Did you get 1/25 like I did? Nice, excellent work there. Okay, this one here. Oh, quotient rule. Hey, these exponents thing, you just got to practice them all year. Algebra 2, you practice them all the time too. So anyways, I'm going to break this one up here too, because remember the coefficients divide into one another, the variable with the exponent divides into one another. So here I'm going to change this to 8/-2 times by, we're just going to break up this fraction here, times by x cubed over x to the -2. Okay, the rule is, well, I'm just going to divide there. That's going to equal -4. Okay, here, this here is going to be the same thing as x cubed divided by x to the -2. So here, remember, you take the exponents and you're going to subtract this division one from the numerator here. So 3 minus -2. Ooh, tricky, tricky. 3 minus -2. So is it going to go down from 3 or up? Subtracting a negative means addition. 3 plus 2 equals 5. So I got -4 times by x to the 5th power. Whew, those were tough. Those were tough here, okay? So I'm guessing maybe a lot of people watch 8/117. If so, hello. And maybe you watched the whole thing. That's fine too. But hopefully you feel like you got a little bit of practicing, which was kind of the goal for us this Tuesday. Okay, thank you for watching. Welcome back. Hopefully you checked out your quiz grades and message me if you have any questions. Take care, guys, and I'll see you tomorrow, Wednesday. Bye.